Here are solutions to homework set number 8 for ECE 341. This homework covers gamma, Poisson, and normal distributions. Now the first problem is, suppose I've got player A, or let A be an exponential distribution with a mean of 30 seconds. So what that means is the PDF kind of looks like this. It's decaying as e to the minus 2 over 30. The mean, right about here, is 30 seconds. Let B be the time until 3 customers arrive. Determine the PDF for B using Laplace transforms and find the result at 20 seconds. Well, the Laplace transform, or moment generating function, same thing, of A is an exponential, mean of 30 seconds, so that's 1/30th over s plus 1/30th. That's the time until 1 customer arrives. Time until 3 customers arrive is just that cubed. So that'll give you the PDF. The PDF looks something kind of like this. What I want to know is at 20 seconds, what's the area to the left? One way to do that is to find the PDF. I can use the table of Laplace transforms. A form of s plus b cubed, 2 over s plus b cubed is t squared e to the minus bt. To put this in the same form, I'm going to factor out, put a 2 on top and divide by 2 to make it cancel, factor out the 1/30th squared. Now this is in the same form as my table, so it's my constant times t squared e to the minus t over 30. So that's the value of the PDF at 20 seconds right here. Let's see. Problem 2 is repeat using convolution. So here what I can do is give the PDF for A. It decays exponentially as e to the minus t over 30. I'm going to take it out to 500 seconds. That gives you like e to the minus 20th. Not quite 0, but pretty darn close. That's the time for one event. 2 events would be the convolution of A times A, and you have to do times dt. Since this is continuous time, I'm integrating. B would be the time of 3 events, so that'd be 2 plus 1 gives you 3. That'll go out to a whole bunch of places. To plot it, I'm going to truncate B to the length of t. That lets me plot it, and here's what the PDF looks like. At 20 seconds, I'm right about here. Since I start from 0, 0, everything's off by 1. So at 20 seconds, it's b, or 20 over dt plus 1. So 0 means 1. Well, everything's offset by 1. So that gives me this term, which is pretty darn close to the exact answer. A little bit off because my sampling rate is only 0.01. I only took it out to 500, so it's going to be a little bit wrong. Problem 3. Problem 3 looks at a Poisson and looks at a Poisson distribution. So this is the probability that 2 customers arrive within 60 seconds when you have an exponential distribution of 30 seconds. So here I've got an exponential. Again, the mean is 30 seconds. Find the probability that 2 customers arrive in 60 seconds. So right here at 60 seconds, what's the probability that the 2 arrive? So one way to do that is Laplace transforms. Here I didn't specify how you're supposed to solve it. Could use Laplace transforms. So here's the PDF. Here's 1 customer, 2 customers. If I integrate, I get the CDF. So this is Laplace for integration times 1 over s. Take the inverse Laplace transform. So I get plug in s equals 0, and I get 1. Plug in s equals minus 1/30th. Cover up this term, and I get A. B you got to work for. So putting this over a common denominator, solving for B is minus 1. So here's the partial fraction expansion, which has the Laplace transform of 1 minus 1/30th t e to the minus 30t minus 1 e to the minus t over 30. So that's the CDF. that kind of looks like this. It goes from 0 to 1. If I plug in 60 seconds, I get what the area of the curve is. Area of the PDF to the left of 60. And it's 59%. So a 59% chance I'll have 2 customers within 60 seconds. One way to solve. Second way to solve is, here's 1 customer, 2 customers, do convolution. And if I plot it, I guess I did do the plot. It looks kind of like this. That's your PDF. What I want to know is at 60 seconds, what is the area to the left of 60? So one way to do area is integrate. Numerically, it's the width times height. So take the sum of all the a's, that gives you the height, times the width, that's the area. Also 59.4%. Again, not exact because I'm using Euler integration. Runge-Kutta would be better. Trapezoid rule would be better. But make the step size small, it'll be close. Problem 4. 4 looks at a Poisson and a binomial distribution. So in Dungeons and Dragons, if you roll a natural 20, you do double damage. That's a critical hit. What's the probability of doing 3 critical hits in 30 rolls? That is a binomial distribution. So I've got 30 rolls, choose 3. Probability of hit is 1/20th. Probability of a miss, not a critical hit, 19/20ths. Multiply it all out, 12.7% chance of doing 3 critical hits in 30 rolls. Poisson is a way to approximate binomials. When these numbers get large, it gets kind of hard to calculate. With a Poisson, I've got a parameter lambda, that's n times p, which is 1.5 in this case. The PDF for Poisson distribution is 1 over x factorial lambda to the x e to the minus lambda. So with that value of lambda, for x equals 3, it's 1/3, 1 over 3 factorial, 1.5 cubed, e to the minus 1.5, 12.5%. About the same. So the Poisson approximation is used when the binomial just gets bad numerical properties. So like, for example, if I made n, so this is n and p, n is 30, p is 1 over 20. If I made that 1 over 2,000 and 3,000, then n times p is the same. I'll get the same answer. But with the binomial, it gets harder to calculate because they have 3,000, choose 3. 3,000 factorial usually makes most calculators blow up. But that's problem 4. Problem 5 looks at a normal distribution. Suppose I have 3 variables, each has a normal distribution. What is the PDF of f, and what's the probability that f is more than 30? Well, with normal distributions, when you add them, the means add, the variance adds. So the mean of f is 25, the variance of f is 61. Take the square root, I get the standard deviation of f. So here's what f looks like. It's a bell-shaped curve. The mean is 25, and the standard deviation, about this far, is 7.8. What's the probability that'll be more than 30? So what's that area? To figure that out, I calculate the z-score. That is, how far is 30 from the mean in terms of standard deviations? It is 0.6402 standard deviations away. From a standard normal table, I can then convert 0.64 to an area, and it gives you an area of 26%. So a 26% chance the sum will be more than 30. I can check using Monte Carlo. I'm going to pick a random number. X is a standard normal distribution. The mean is actually 5. The standard deviation is 5. The mean is 15. Y has a standard deviation of 6, mean of 10. Add them all up and check. Is the total more than 30? If it is, I get a win. So if I do that, I got 26%, theoretically 26.1. So again, that matches up. Problem 6. If I add 3 normal distributions, again, the mean will be the sum. Mean is 30. The variance will be the sum. Variance is 110. Take the square root, I get the standard deviation. And this is the oddity of normal distributions. It's the variance that adds, not the standard deviation. So when I'm done, I've got a normal distribution. Get normal plus normal is normal. Now the mean is 30. The standard deviation is 10. I want to know what's the probability of being more than 40. I want to find out what's the z-score. And the z-score is how far 40 is from the mean in terms of standard deviations, 0.95 deviations away. From StatTrack, or normal table, I can convert that to an area, 17%. I can repeat using Monte Carlo. Add 3 random variables together. If the mean is bigger than, or the total is more than 40, count it. If I run that 100,000 times, it's 17.1%, 16.9%, 17.1%, basically what we're calculating. So that is homework set number 8 for ECE 341.